So we are on 7.2 homework in the textbook. Starting with number 1. So they give us this big situation. They want us to write an exponential growth equation to describe the situation. Okay, so we know it's going to be b times g to the x, that format. Okay, so whatever we begin with times the growth factor raised to the time. And so we are beginning with 11. So for part A here, there's 11 of these fish. So that's the b. The growth factor, they're telling you that the population triples in size. So after 1 year, it would be 3 times the size. So it'd be times 3. And every year, it's going to triple after that. And so that's going to be raised to the time, which we don't have. Okay, so there's our equation. You could write equals. Technically, this is an expression. So if you wrote equals total fish, you could use a variable for that, create an equation. But this is what we're looking at. 11, which is the original, the starting point, times the growth factor of 3, because it's tripling, raised to the amount of time. So, letter B, how many of these are there after 2 years? We're just going to take this. We're going to raise it to the second now. Well, 3 to the second is 9, and 9 times 11 is 99. Now, one common mistake, first of all, you can put this all in the calculator at once and it will handle it, but one common mistake is people try and do it in their head and they multiply first and then raise by the exponent. So they want to do 33 to the second power. Just remember your PEMDAS exponents first. So you have to do 3 squared first. That's 9 times 11. It's going to give you a much different answer. Okay, and we also had part C. How many were there in 2000? So if we look back to this started in 1995. Okay, and we are doing this each year after. So if it's the year 2000, be careful, don't put 2000 into the equation. It's been 5 years since 1995, so it's 11 times 3 to the 5th power. So we can just go ahead and plug this all right in. 11 times 3 to the 5th. Oops. 11 times 3 to the 5th. And we're going to get 2673. Okay, moving on. Question number 2. We're going to copy the table on the right and we're going to fill it in using y equals 50 times 1.2 raised to the x. We've got x and y. 0, 1, 2, and 3. So first of all, just examining this, making sure we understand what this is. 50 is our starting point for whatever this is talking about. Growth factor is 1.2. That's a 20% increase. Okay, 20% is 0.2. And when it's added on to 1, that's 120%. So after 1 year, 50 will go up to 120% of what it used to be, or go up 20%. So that's what 1.2 represents. So if we plugged in 0, 50 times 1.2 raised to the 0. Notice we get 50. Why do we get 50? Because anything raised to the 0 is 1. 1 times 50 then is 50. 50 times 1.2 raised to the first. Well, that's really just 50 times 1.2. That's 60. Now, if this was linear, okay, not exponential, but linear, and we saw, oh, it went up by 10, then it's going to go up by 10, then it's going to go up by 10. This is not linear. So when we raise it to the second power, now we went up by 12, so we went up by more. And when we do the last one, third power, it goes up even more. Okay, so we filled that in. Question 3. $3,000 is invested. 4.5% is the annual yield, which is our growth factor. Okay, the new growth factor now, if you think about the equation that we were using in 7.1, principal times 1 plus the rate raised to the time. This is the growth factor in here. Principal is what we're beginning with. Then this is the growth factor raised to time. So because the money is growing, you're going to have over 100%, and that's what the 1 is. So looking at this one, first of all, 4.5%, we need to turn that to a decimal. 2 to the left is 0.045. And when you add that to the 1, it's 1.045. And that is part A. That is the growth factor. If you just put 0.045, that means you'd be multiplying by 4.5%. And you'd actually be finding 4.5%. So the number would be getting smaller because you're actually taking 4.5% of something. We need it to grow by 4.5%, so we need the 1 in front to make this go over 100%. Okay, part B now, let's actually go ahead and plug the numbers in. We're going to find the value of the account after 2 years. So my principal is 3,000. My growth factor is 1.045. And my number of years is 2. So I'm just going to go ahead and plug this right in. 3,000 times 1.045 raised to the second. We get $3,276. We're only going to go 2 spots here because we're talking about money and we're not rounding it up. So 0.7. So question number 5, we're plugging in these numbers for X, Y, and Z. But if we look carefully, we really don't have to do much math here because anything raised to the 0 is 1. And so that's really what we're looking at here on 5 and 6. So for 5A, regardless of whether I plugged in any of these numbers, they're going to be raised to the 0, and so the answer is just 1. Now letter B, this second one that's raised to the 0 is going to be 1. It's just going to get multiplied by whatever that first one is. So this is really 17 times 1. So my answer there is just 17. And letter C, you could go ahead and plug in the numbers. 7 plus 7 is 14. No, it's not 7, 17. 17 plus 17 is 34. Raised to the 0 is 1. But it really doesn't matter because these are in parentheses. That's the first thing you're going to do by order of operations. And then whatever number you get is going to get raised to the 0. And it doesn't matter what number is in there. When it's raised to the 0, it's 1. So for letter C, you don't have to show all the work. It's just 1. Number 6, letter A, anything raised to the 0 is 1. Doesn't matter what number we put in. Letter B, if you look at this, both of these are raised to the 0, so both of these are 1. This is really 1 minus 1, so my answer is 0. And letter C, once again, it doesn't matter what's in here. You can plug in any numbers you want. You can plug in the ones they gave you or anything else, but regardless, whatever you get in here, when it gets raised to the 0, the answer is just 1. Okay, number 7, explain why these are not equal. So since -5 in parentheses raised to the 0, since it's in parentheses, that means this whole number, -5, is being raised to the 0, so it's 1. -5 raised to the 0, okay, is different. This is only attached to the 5, and so the 5 becomes a 1. 5 to the 0 is 1, but this negative is separate. It's not in parentheses. It's basically like a -1 being multiplied, and so my answer here is going to be -1. And if you're going to explain it, you could say the order of operations, something along those lines, but showing your work here is going to explain it as well. Okay, this is like multiplication, so really this is like -1 times 5 to the 0. You do exponents first, so really this is -1 times 1, which equals -1. Okay, number 9. We're going to use this equation. We're going to make a table. And we got to do x is 0, 1, 2, 3, 4. So basically we're just going to go ahead and fill in for y. So we're plugging in for x, so it's going to be 0.5 times 2 raised to whatever x is, so raised to the 0. So before we even hit enter, let's think about it. 2 raised to the 0 is 1, so 1 times 0.5 should give us 0.5. Now if we do 0.5 times 2 raised to the first, because we're plugging 1 in for x. Anything to the first is itself. So this is 2 times 0.5. 0.5 is a half. A half times 2 is going to be 1. 0.5 times 2 raised to the second. That's going to be 4 times 0.5. Half of 4 is 2. Raised to the third. Okay, that's 8. 2 to the third is 8, and half of 8 is 4. And 0.5 times 2 raised to the fourth is 8. That's part A. Part B, they want you to graph those values. We didn't have to do part B. Okay. If you were going to graph it, though, you would just make a quick chart like this. You got your x's running across the bottom, your y's running across the top, and you graph it. So no big deal. I just saved you a little time. So we're jumping over to 13. They give you an equation that's modeling the population, which means it's estimating what the population is going to be for however many years it is after 1860. All right, the graph shows you the actual population. So the equation is going to estimate it, and then we've got the actual numbers, and we're going to compare the two. We're going to see how close the equation came to the actual numbers. So 13a, they're going to ask you specifically what these numbers in the equation represent. If you see the 34,277, it's sitting in the spot for b, which is the beginning amount. So that's going to be, 34,277 is the population in 1860. That's what we started with. And the other thing they want you to explain is 1.04. That's the growth rate. Which, if we examine further, 1.04, that 0.04 is 4%. So you started out in 1860 at 34,277 people, and it's growing by 4% per year. Letter B, what does the equation predict the population will be in 1960? So we started in 1860. 1960 is 100 years later. So we're going to go ahead and take this equation, and we're going to plug in 100 for x. And we're going to get this big number. And we're talking about people here, so we're not going to worry about the decimal. This is not money. So we're looking at 1,731,158 people. By how much did the actual population deviate from the prediction? So if we follow 1960 on the chart, we were supposed to be at this number, but we were actually at this number. So really pretty darn close. The estimate compared to the actual. And so if we want to know how far did it deviate, that means just how far off was it. So I'm going to go ahead and subtract these numbers. I don't want a negative number. I'm just talking about how far off it is. So I am going to subtract the bigger number first. So we were off by 22,789. So pretty close, really. Part C, use the model to predict the population in 2030. So first thing we need to do is figure out how many years that is since 1860. So we go all the way to 1960. That's 100 years. We already did that. Go up to 2000. You're going to add another 40 years to 1960. So we're at 140 years. And we're at 2000. And then add another 30. Okay, and that is going to be 170 years. So we're going to go ahead and plug into our equation. But we're going to plug in 170. And we get 26,956,933. So in 15, they want you to graph y equals 2.5 raised to the x for these values. So the first thing that I need to do is just make a quick xy chart. And then once I've got it, I'll put it on a graph. So they want me to go all the way up to 5. So first thing I need is my x values so that I can plot this. So 2.5 raised to the 0 is 1. 2.5 raised to the first is 2.5. 2.5 raised to the second is 6.25. 2.5 raised to the third, 2.5 raised to the fourth, and 2.5 raised to the fifth. So these are the numbers that I have to put on the graph. So as I make my graph, I'm just going across 1, 2, 3, 4, 5. So starting with 0, 1, 2, 3, 4, and 5. Going up, when I get to 5, I need to be able to fit 97. So I got to get all the way up to 100. So I'm going to call this 25, 50, 75, 100. You can count by 10s, 20s, whatever's going to work for you. But at 0, we're all the way down at 1. So don't put it up here halfway to 25. It needs to be real low, close to 0. At 1, we're at 2.5. That's still really close to 0. At 2, 6.25. So let's start thinking about what's halfway to 25. That would be 12 and a half. So 6.5 is still below that. So when I get to 2, I still got to be below halfway. When I get to 3, again, halfway to 25 is 12 and a half. So 15 is going to be a little bit higher than half. So from 3, I'm going to go up just a little bit. So really, this thing's barely increasing until I get to 4. And that's how exponential growth works. It's going to start off slow, and then all of a sudden, it's going to take off. And so for 4, I'm going to have to be at basically at 40. So here's 25 and 50. 40 is going to be kind of close to 50, so up here. And then all of a sudden at 5, I'm almost all the way up to 100. So it's going to look like that. And you don't have to connect the dots. You can leave it. We just have those single values. You can leave it just like that. All right, that was part A. Let's to graph it. So part B, they want you to calculate the rate of change from when x equals 0 to when x equals 1. Remember, rate of change is like the slope. So we are changing on the top 2.5 to 1, and that's over the course of x just changing by 1. So the change here is going to be 1.5, and that was over just a change of x and 1. And so my rate of change is just 1.5. So from 0 to 1, it changed by 1.5. And then letter C, they want you to calculate from 4 to 5. So again, this is like slope. We're going from 4 to 5. So again, just a change of 1 in the x. But when we look at our y values here, going from 4 to 5, I'm going to kind of even just, for the sake of space here, just do the 97 minus 39. And it's going to be 58. Now, there'd be a little bit of a decimal there, right, if we included everything. But for what they're trying to show you, letter D, what do they tell you about this? Okay, if the rate of change is the slope is this different, it tells you that it is not a line, that it's exponential. The rate of change from here to here was a lot different than the rate of change from here to here. And remember, that means slope. The slope here, very small. If it continued straight, that would be linear. But clearly, the rate of change increases drastically, which means it's exponential. Okay, number 16. We are depositing $3,400 in a savings account with an annual yield of 5%. That's 0.05. So we're increasing, so it's 1.05. Total amount of money in 8 years. Just go ahead and throw the 8 up there, and we'll just punch this right in the calculator. $5,023.34. 17. Suppose a person's birthday is in July. What's the probability that is on July 4th? So first of all, we need to know how many days are in July. There's 31. So probability is always out of the total option. So there's 31 days. How many days could it be there? Could it be July 4th? There's only one July 4th, right? There's a July 1st, 2nd, 3rd, all the way up to 31. So the probability of it being on July 4th is a 1 out of 31 chance. Part B, someone's birthday is in March. What's the probability that it is before the 10th? Again, there's 31 days in March. So before the 10th would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different numbers before the 10th. 9 out of 31 days would be the probability. Okay, we jump to 19 next. So in this triangle, we see AB is 9. I'm just going to go ahead and sketch this and fill it in as we go. AB is 9. They tell you AC is 20% longer. So if we take 20% of this and add it on, we're going to get to here, which is the same as finding 120%. So 9 times 1.2, because it's 20% bigger, I'm adding 20% onto it. It's 120%. That would be 10.8. Okay, its side AC is 20% longer than AB. And then they tell you BC is 45% shorter. So I could find 45% of this and then take it off because it's 45% shorter, not 45% of the size. Or if I'm taking 45% off of it, if it's 45% shorter, think about 100 minus 45%. That means it's actually 55% of the size. So you either take 45% of this, multiply by 0.45, and then actually subtract that number off. Or again, think about if it's 45% shorter, I'm taking 45% off. That means it's 55% of the size. So if I want to find that number, I'm doing 10.8 times 0.55. That's 5.94. And the final question says find the perimeter. So I'm just adding up those sides. 9 plus 5.94 plus 10.8 is 25.74. Last question, number 20. Which expression does not equal this? So let's start with the original and distribute this. I'm going to get negative 3x, and I'm going to get positive. 2 negatives make a positive when I'm multiplying 3y. And so I can see that answer right here. Now these other ones with parentheses, if we distributed, do we get back to the same answer? Probably, maybe. But right away, when I look at letter B, this 3y is positive, but the 3x is negative. And there's no way to simplify this. There's no parentheses. This isn't changing. This is the final answer. And so it is never going to equal this. And so I know right away that letter B is the one that is not equal to it. Here, if you distributed, you'd get a negative 3x to match. You'd get a positive 3y to match. And same thing here. But letter B is the one that is not equal to it. So we can stop right there.